Okay, so now we're going to talk about Taylor polynomials, and we're going to use those to approximate values of functions. The thing is, here we have already been doing this. We did it actually quite often when we use the equation of a tangent line to approximate values of functions. Remember, we used like y minus f of c, whatever that was, equals the derivative, say it was 10 times x minus c. And we use this to approximate a function. So this is actually a Taylor polynomial with degree 1. Polynomials are these functions where the variables have non-negative integer exponents, and their degrees are the highest degree. So we could somehow come up with maybe better approximations by using higher degree polynomials. And it's kind of obvious why they may make better approximations, because most of the graphs we study are curved. Tangent lines are not. But as soon as we make the degree higher, they start to become curved, and you can see they're going to hug the graphs better. So we're going to start with something we already know how to do. We're going to determine the tangent line to the graph of the square root of x at 1, 1. So if you remember, we can now use that tangent line to approximate a square root of something close to 1. We're going to do square root of 2, which isn't that close really in calculus. Maybe 1.1 would have been better, but we're going to do that anyway. So you remember what the equation of a tangent line looks like. And I'm just going to bring this f of c over. So we have y equals f of c plus f prime of c times x minus c. So we have to find the c is going to be 1, x equals 1. You know, f of 1 to 1, it tells us right here, or the square root of 1 is 1. The derivative of the square root of 2 is, this is really lazy, use wolfram off of that. First derivative of the square root of x is 1 over 2 root of x. So if you plug in 1, you're going to get 1 over 2. And that's it. That's the equation of the tangent line. If you look at my graph over here, that blue line should be y equals 1 plus 1/2 times the quantity x minus 1. And you can see it does hug the graph pretty well around this area. But as you get to 2, you can see the gap between the two graphs are widening, which means your approximation based off the tangent line is not going to be as close as it would be, say, if we used a 1.5. So what we're going to do now is bring some curvature to that tangent line. And it's a formula, a big, long formula, but we already have most of the formula here. You just follow the pattern. This is called a Taylor polynomial. This is degree 1. If you want to make it degree 2, you just start expanding on the terms. So this is the very first term. It has x to the 0. The second term is this, f prime of c times x minus c to the first. So I'm not changing anything. I want to add one thing, though, that you've never seen before, but you wouldn't even show this really anyhow. This is over 1 factorial. 1 factorial is 1, so this and this are the same. The reason why I wanted to show you that, though, is because that's going to be common in all terms. As a matter of fact, this is, you could even think of this as x to the 0 and 0 factorial. 0 factorial by definition is 1. So I'm going to get rid of those two just to not confuse anybody. And remember what factorial means. 8 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. 1 factorial will be 1. So there's your quick factorial review. So if I want to add a term to this polynomial, I'm going to do this. Plus f double prime, so I just added a derivative, over 2 factorial x minus c squared. So all these are common. First derivative right here, first degree, 1 factorial. Second derivative, second degree, 2 factorial. So what this would give me is if I plugged in 1, just like we did for our linear approximation, that would give us a parabola to approximate this function. And so all you have to do is f of 1 is still what we got. F prime of 1 is still whatever we got there. F double prime of 1, here's the derivative. You plug in 1, it would be negative 1/4. And then x minus 1 squared. So to demonstrate this, here's my tangent line. You can see it right here. Now I'm adding this second term. Here's the second derivative at 1 over 2 factorial. Watch what that looks like. Now it's curved. You can see it's a parabola. If we zoom in closely, we can see, you see that blue line? That was our linear function. These two red lines, I don't know which is which, but there are the second derivative polynomial and the original function. You can clearly see how much closer that approximates the graph. It hangs on it for a much longer time and much closer. So that's what that does for us. Now I'm going to add one more term to this Taylor polynomial. So let's move this over. Let's make it a third degree polynomial. So we're going to have y equals, nothing changes. This was our first degree polynomial. This was our tangent line. Then we added this next term, second derivative over 2 factorial times x minus 1 squared. Now the third term, you just follow the pattern. The third derivative at 1 over 3 factorial times x minus 1 cubed. So third derivative is this. If you plug 1 in, you'll get 3/8. So this is just going to be 3/8 over 3 factorial. So third right here, I'm going to scroll over. That was the second degree. I just added this third term in. I'm going to allow that to graph now. I'll get rid of this. So now you're going to be able to see how much closer that follows the graph. The other one. So that was the second degree is flashing on and off. You can see the third degree is much, much closer than that was. And then we'll can do the fourth degree. I already did it for you. That's even closer. And we can go on and on and on and get it closer and closer and closer. So that's the whole process behind it. Hopefully that gives you some kind of background so it will make sense as you're doing it. My next video is going to be a more, I guess, concrete example. We'll just follow the formulas and see what we get. So until then, I'll see you.